So my name is Luckow. I'm leading innovations and emerging technologies at the BMW Group IT. And I spent most of my time right between the advances in computing, in AI, and BMW applications. And what I would like to do is to show you some examples on some stuff we are working on, and also share some of our thoughts on the quantum ecosystems, on benchmarks, and it's a quantum software form after all, also on quantum software, this time more from an application user perspective. Okay, so let's directly get started. So maybe BMW, right? So we design, engineer, manufacture, sell cars. We have a lot of connected services, etc. As you probably can imagine, the car is a very, very complex product comprising of software and hardware. And we sell more than 5 million vehicles per year. And for that, we have more than 30 manufacturing plants. And now you're asking why you're giving me your company presentation here. But what I would like to highlight here is it's a very complex ecosystem to keep on track. So there are ample opportunities for computation, for simulation, for AI, for optimization, and we'll touch on some of them during that presentation. And that brings us to our computation challenges here. In the past, our high-performance computing infrastructure, we have been continuously investing and upgrading that infrastructure. Currently, we have more than 400,000 cores, mostly hosted in Sweden and in Iceland. And often we get the question at the IT is, hey, why do you have to extend your computation capabilities all the time? Will this ever stop? And the answer, obviously, to that is no, right? Because new computation capabilities enable us to simulate stuff that we couldn't think of before. For example, we talk about material science in the quantum chemistry domain, but also many, many classical simulations. So we have different simulation types. We are now also simulating many parts of our manufacturing process, for example, forming. Here we have an electric engine. That's also, let's say, a fairly new game for us, not as new as for maybe some others. And we have more various types. This is probably hardly to see, those are our crash simulations. And we also see that those workloads get much, much more heterogeneous, right? Here those are our classical physics solvers, right? Partial differential equations, but AI is coming big time, right? So we are going to use AI for example, approximating many parts of the simulation process in the future there. So on the near-term side, we have to deal with nodes, but also with specific domain-specific computations, for example, on GPUs for AI, but also for basically physics simulations. And now the question is, right, can quantum computing provide us maybe some new capabilities to deal with the computational challenges of the automotive industry? And I like Sutton's bitter lesson here, right? Because when we think about AI, we maybe think about many handcrafted algorithms, but here the key is, right, progress in AI comes actually from leveraging scale and computational powers. And when we think about artificial intelligence in general, generative AI, then we are basically talking about scaling laws, and we're talking about how much compute can we actually throw on those models. That goes so far that we are thinking about, not BMW, but the whole community is discussing very intensively, hey, how much power can we put together and put the data center right next to that in order to operate 1,000 GPUs, and in order to actually get the AI capabilities to the next level there. The question now is, how long can this be sustainable? And that brings us to the field of quantum computing. So those are the areas that we are looking at. I already spoke about AI, no matter whether it's sixth generation, and we have ample use cases of that. It can be assisting many knowledge worker disciplines, summarizing text, generating content, etc. I don't want to spend too much time here. Material science, that's obviously a domain that we are very hopeful that quantum computing can deliver the biggest impact there, because we have many chemistry problems, many material science problems that we are not able to solve with classical computing infrastructure. To give you two, one is obviously the battery. The battery is a highly differentiating component, so the more power you can pack into a battery cell, the lighter you make it, the cheaper you make it. It's really the key differentiating factor in the electric mobility. And the other one, we are also investigating hydrogen fuel cells. As a matter of fact, we already announced a product, so we have the power of choice. And also there, we already did a successful project, which I'm going to talk about in a bit. We already talked about high-performance computing simulations. And last but not least, I know there's probably not so many of your concerns here in the audience, but post-quantum security is a key thing because we do have a product out there that is to some extent updatable, but potentially want to avoid that a quantum computer compromises the security of our vehicles. So where are we with quantum computing? So we try, and there's also a task of our team here is to keep in close contact with the ecosystem to really understand what the current state of the quantum computing community is. And we're always kind of between hype and hope, how Scott Aronson put it. Right? And one time we do see on a daily basis when we're working on the technology that the NIST hardware limitations are clearly there. And we also see that we have a huge demand and huge opportunities, for example, with classical algorithms in the AI space. At the same time, we obviously see also a lot of progress that's being made on error correction and scaling the current hardware things, but it's just not tangible enough that we can directly say, hey, let's put that into production within 1 or 2 years. On the algorithm side, also that's something that's obviously at the end of the day that matters, and I think the previous speakers both highlighted that there is some more progress and more creativity probably useful there, but we also see breakthroughs with existing algorithms. For example, Shor algorithm was improved last year, so you need to have now much fewer gates and actually make it happen. And on the ecosystem side of things, I think just looking at this room here, I mean, the ecosystem is going strong, right? Right now it's mainly driven by government investments there, but that maybe changes once we see an advantage there. So how do we think about research or our part in the ecosystem there? So typically, we have been focusing a lot on translational and applied research, basically, working with the ecosystem, bringing things into our vehicles, into our processes there. But we do realize, with quantum computing, there's a lot of more, let's say, more foundational research that is required there. So this is Pasteur's quadrant, right? So here we have the conservation to use, and there we have kind of curiosity-driven research. And what we hope, and that's why we engage with all of you, is to inspire basic research with some of our problems that we think are worthwhile solving, because they have a big impact, not only for BMW, but maybe also for other industrial companies there. And obviously, translational research is taking ideas, taking work from the community, benchmarking that in a real-world context, and see how far we can take ideas. So BMW is also a founding member of the Quantum Technology and Application Consortium, which is basically 13 companies distributed across Germany, and some are also in Austria there. That dates back to 2021. Back our Chancellor Angela Merkel encouraged the companies to kind of get together and really form a strong voice and guide the community with respect to the applications of quantum computing. Okay, so what I would like to do now is to talk about a bit more in detail on the applications, and then talk about benchmarks and software. So, and for the applications, I did bring a movie.
But companies are already preparing for a future when quantum computers catch up to their expectations.
We want to be ready when the machines are ready. So we do not want to wait until the machines are ready. It's not just about using quantum technologies because there are quantum computers out there. We want to have real valuable algorithms and prediction.
One of those applications takes place inside BMW's wind tunnel. The company tests the aerodynamics of its cars here. This is a light breeze, 30 kilometers per hour. It could go up to 300, but I think maybe not for today. In addition to tests in this wind tunnel, BMW also currently uses classical computers to simulate aerodynamics. This can be an expensive and time-consuming process, one that quantum computing could transform.
So you would reduce one iteration from days to minutes or seconds.
How does that work? Are you creating algorithms now
Yes.
for computers that don't exist?
They exist. You can, on a very small scale, you can't calculate the whole car. So you can, for example, you can calculate 1 wheel, but it can show that the principle works, and we write code which we can scale when the machines are ready.
BMW is working on these algorithms with a French quantum startup called Pascal, and they're partnering with several companies to prepare for a quantum future. A future that I can't wait to see. They wasn't that, wouldn't they? They go everywhere.
Yeah, so the whole show is available online. And as you saw there, right, I mean, we typically invest quite some by heavy-duty devices, like, for example, our wind tunnel. And as you can also imagine, the time that the vehicle can spend in the wind tunnel is very limited because it's also very expensive. That's why we do simulations, right, for CFD. I mean, the aerodynamic is just one example of a CFD simulation. We do many other aspects. This, for example, is the cooling of an electric engine. And there are some promising algorithms on the theory side of things, for example, HHL. Concretely, and it was briefly mentioned in that clip, together with Pascal, we worked on an algorithm that's called differential quantum circuit. We are also looking into some quantum-inspired methods based on tensor networks to actually approximate the underlying physics there. Currently, the state of the art is we are far away from the real car, so we are more working on kind of simulating the airflow around a circle. But if you want to learn more, you can use those two publications there. So, I already spoke about the fuel cell. There we investigated together with Quantinuum and Airbus the variation quantum eigensolver. Also there, the scale is rather small, right? So 4 electrons, 4 orbitals, I think was the scale that we were able to simulate there. But having said that, it's an important problem to solve. Optimization. And I gave you the numbers of the scale of the company there. One of our first problems that we solved was the robot path problem. So basically, before you deploy a robot in a manufacturing line, you want to optimize the orchestration, maybe between multiple robots, multiple arms. And in order to do that, you have basically a humongous optimization problem. That's where we actually we demonstrated by using quantum computing that we're able to model the problem. We are now using a more classical solver to actually solve that. But a lot of value for us is really understanding and modeling the problem, and then we can scale it across all our manufacturing sites. So this is another problem. It's capacity planning. So what you see here is a big stamp, right, that creates parts. And typically we have many plants, and most of the plants, they have like a body shop that basically is creating those parts. And now the question is, what part should be built in what body shop facility, taking into account logistics costs, taking into account, whether the tools are available there, what vehicles built where. So it's always an infinite optimization problem. Once you solve this, someone from the business will come up, but did you consider this constraint in that exercise? And then typically we don't, right? But I mean, let this change there. So, and I will talk a bit more about our benchmarking activities with respect to quantum machine learning. We just heard from Josh what the state of the art there is. Nevertheless, we do think it's a valuable problem to pursue. This is not rendered on a quantum computer, but this is basically our digital factory in Debrecen. So before we build a car, before we build a factory, we actually create a virtual digital twin of the factory that enables our planning analysts to actually design the working steps. Okay, so now I would like to talk a bit about benchmarks, because that's what we actually were asked to talk about. And benchmarks is something that is always either you love it or you hate it, right? But we do strongly believe that benchmarks are essential to drive the community forward. What is a benchmark? It's basically workload, it's a data, and it's a metric that's actually used to compare systems. And in the past, we have been seeing many successful benchmarks actually driving the progress of the community. One, for example, is the ImageNet benchmark, right? That was maybe created 15 years ago. Fei Li, right, back in the days, she put together this big, humongous data set of images, more than 1 million images in 1,000 different categories. Graduate students that had to label that data, and no one ever thought that this data set could actually be used to create an image classifier, right? But it only took a couple of years until Alex Wisniewski, a student of Jeffrey Hinton, came along and actually solved that benchmark. But would have not been this ambitious benchmark there, he probably would have never solved that problem because he didn't have the data, he didn't have the metrics, and that's kind of guided a lot of the progress there. And obviously, in particular in the AI space, we see how short-lived benchmarks nowadays are. Nowadays, no one cares about ImageNet anymore, except the quantum computing community, right? So ImageNet or a small subset of ImageNet, but then the AI space is basically solved. The high-performance computing space, right? You have LINPACK. That's the benchmark that's been used to determine whether a machine is in the top 500 list or not. And there's obviously, with every benchmark, this intense discussion: is this representative or is it not? And obviously, the same will also be happening in the quantum community. So there are many benchmarks, metrics. They are all exciting. For example, we have system-level metrics, we have algorithm-level metrics, we have application-level metrics. To be very honest, right, the boundary between algorithm level and application level is kind of fluid, right? Because many benchmarks you run on an algorithm, you typically do that on a proof of principle demonstration, so not a real applications. The organization principle here is if the metric is more concerned with the applications there. So we have the Q-score that measures the performance of MaxCard. The QEDC has a very comprehensive benchmark suite with optimizations, chemistry, simulation problems at hand. Supermarket is also a very comprehensive benchmark suite. So now the question is, what is our take on this benchmarking game? All those metrics are to be somewhat technical, but we always have a difficult time to really translate what does a Q-score of X mean, for example, for a specific business problem, business challenge at hand. And we also realize that the challenges are changing all the time. Oh, I forgot the tools. And that's basically why we came up with a framework. It's open source, it's available on GitHub, which is called Quantum Application Level Benchmarking Framework, Quark short. And the idea there is to actually simplify and accelerate the creation of quantum computing benchmarks. Basically, the framework will help you modularizing the benchmarking workflow. It will help you to capture the data, and it will ensure reproducibility, and also that you can kind of, in this very dynamic world, enhance and improve your benchmark. Yeah, and you can argue, right, is it too soon for application level benchmarks? It was already there in 2022. We are thinking about, is it too soon or too late? But if you never get started, you will never reach the goal. So Quark is very modular. Initially, we had a very, let's say, rigid pipeline that was focusing specifically on optimization problems. So modeling the problem, mapping it to a specific quantum framework, could be QA/OA, could be annealing, plugging in different solvers and different devices there. And with Quark 2.0, what we actually did is we generalized that framework. So basically now you can come up with your own module structure. I mean, obviously, we have a good recommendation, for example, for all those quantum machine learning workflows, right? For QML, like for any data-driven applications, you not only need to have the problem model, you typically operate on a data set. We're also working on some exciting capabilities with respect to data sets. You need to think about the data transformations, different types of circuits, and different training methods. And I would like to specifically go to one example here, and that's the synthetic data example. I mean, as an ambition, I put our plant here, right? And you see the bounding boxes. This is actually synthetic data, so we use a mix there, another project, right? Of physics-based rendering using the NVIDIA Omniverse engine, and we also use diffusion models and other types of generative AI to actually create a higher variety of synthetic data there. Well, now for quantum computing, we're using, let's say, some more small-scale data sets, right? We're also using image data, which is very, very simple. We use some finance data from the Yahoo stock data, and basically in this framework, we have a pipeline for generative modeling set up. So this is actually on how the data looks like. You see two-dimensional, so rather simple, but we are also working on kind of compressing more complex data, like the ImageNet data set, and making it available in Quark as well. So how does the benchmark pipeline look like? I mean, there are different, don't want to go into too many details there, different ways to actually prepare that data, discrete, basically then you have to discretize the feature space, or continuous directly plugging the data points in there. Quantum machine learning, like any machine learning, is a bit of black art, what kind of transformation, standardization methods you apply. We were, for example, very successful in that small-scale experiments with this probability integral transformation, right, that basically converts a distribution into a uniform distribution, and that worked very nicely with this copolar circuit that we also have available in the benchmarking framework. And more details are in that paper there. I also have a picture of the copolar circuit here. Right, so this is the circuit of that one. There's roughly 36 parameters, so not too big, and we implement that with Qiskit. I'm just seeing I have to update that because we also have a penny lane implementation of that circuit. And we also investigated different training methods. What you see down here, it's a generative adversarial network, but we also investigated, for example, quantum circuit Born machines. And let me show you some results. So this is the training process after how it should be done. You see how the model learns the different shapes. We noticed the X shape is much more difficult to learn than the O shape. And you can also see we tested different parameters, combinations in here. So that's kind of the model quality dimension. The other dimension is how fast can we be, and that's at the end what matters, right? Because we want to enable rapid experiments. Here we compare GPU-based simulation with Q-quantum, with, let's say, back in the days, at traditional CPU-based simulations, we're able to have a speed up of, I think, roughly 300. So Quark is available online. Just this year, we extended that. We have new exciting problems. Here we have a maximum independent set problem. You can use it, for example, to plan your antennas in the plant or your dealerships or something like this. Also, an exciting problem is, for example, truck loading. Sounds maybe not too excited on the first sight, but that's really what efficiency is all about. How can you efficiently put the cars, taking into account weights, the size of the truck, the size of the different models. So as everything, once you do it on industrial scale, it can become a very complex and exciting problem. And we're also working on different new devices. For example, here's our work here where we use basically a noisy simulation. And so when you go to the GitHub repository, you're more than invited. Those are some marketing numbers there. So I would like to close a bit with some observations on the quantum software space. This is collaboration together with also some folks in the US. And we already heard a lot of today about, we were very much focused on compilers and how to connect the classical and the quantum software stack more efficiently. And I would like to raise the abstraction maybe even a bit more, right? When we think about, how can we integrate that into our compute landscape, into high performance computing, into our AI infrastructure. It's like this observation is that the tasks, basically the unit of works that are being produced by all those quantum frameworks that need to be combined maybe into an end-to-end workflow are highly heterogeneous. So you have a different number of tasks, for example, when you do this, for example, with measurements, with error mitigation. So basically you end up with many, many different experiments there. Input-output data is currently maybe not the most top priority problem, while the machines are still on a small scale. It will eventually become a big, big problem moving the data around. Maybe have smaller, deeper tasks, maybe have wider tasks that require distributed state vector simulations, and the tasks can maybe have different degrees of coupling. So on the other side, what we also see is the infrastructure is becoming more heterogeneous. So now we're maybe working with the cloud access model, and in the future we have integrated quantum HPC infrastructures, and even further in the future we maybe have many, many different GPUs, QPUs, and CPUs that we have to handle. So there are different terms. I think quantum HPC integration is the Munich term. There's quantum-centric supercomputing, that's the term IBM coined. There's distributed quantum HPC. So many people around the world are looking at this space. And the question is, right, how can we actually combine the task parallelism and the requirements of those tasks with the infrastructure heterogeneity? And without spending too much time on there, I would highlight some of our thinking there. Obviously, there are those tightly coupled tasks, right? HPC for quantum, that's what we call it. And this is obviously something that's best left off to the compiler and requires a very low-level integration, right? And obviously, when we think about end-to-end application workflows, we are more focusing on orchestrating on a high level. Then we have the quantum in HPC. It's basically, hey, 80%, 90% of your application will be classical. It will have pre-processing, it will have post-processing, it will have classical machine learning. Right? We heard Josh talking about this exciting paper there where basically a quantum computer is used to train a classical machine learning model. And as a matter of fact, that's one workload that we are expecting will be the key, right? Because quantum time will be scarce, it will be valuable. And how can you kind of amplify that? And we think, this co-placement of classical machine learning on scale and quantum tasks will be the key there. So also exciting. And then the workflows where you basically combine the different steps. So looking at those, we have a paper out here. It's called Quantum Mini Apps and Motives. Let's look a bit more in detail into what are kind of the workload patterns that we see. What are the task dependencies? What are common communication interaction patterns there? Unfortunately, I have not much time to spend here. But key observation: there's more parallelism, there's more concurrency happening both on the quantum but also on the classical sides. We have obviously those standard iterative algorithms. We see much, much more dynamic algorithms. I mean, we heard Bettina call for action there, but it's not like we're doing BQA, classical step, quantum step, classical step, and so on forever. Very likely that will be highly concurrent and requires a proper middleware that manages that. Yeah, and we're working on such a system. It's just a research prototype. It's called basically Pilot Quantum that brings like a task level abstraction to that was designed for high performance computing to quantum infrastructures. And I also have some data on there, but so basically you utilize that for circuit execution. And you can see here it supports different types of backends. We see an example where we use it, for example, in the context of circuit cutting. Also very exciting, you see, you really need to find the sweet spot, and that's like the key thing is, because you need to do properly understand your applications, understand your data and the workload that is actually being generated there, to see when it's worthwhile to go into circuit cutting mode versus, for example, just doing the full circuit simulation. And this is, for example, an experiment where we implemented a QML pipeline that has different stages, a sweeping algorithm and a BFGS optimization stage. So basically mixing tensor networks and more traditional state vector simulations there. And you can see here by going distributed, you can get a speed up. And in order to do that properly, you need to have a good middleware to support that. And that brings me to the end of the presentation now for real. So we require progress in hardware, algorithms, there's a lot of things to do. Applications are easy, there are plenty of them, and benchmarks are here to track your progress.
Very cool, thank you.